Hi, my name is Jakub Horn and I'm working at Cisco as Technical Marketing Engineer. I would like to demonstrate today an SRv6 micro-instruction known as UN. This UN micro-instruction implements a shortest path to a node. It leverages the SRv6 data plane and also control plane without any change. It only requires 16-bit of encoding and hence enables ultra-scale for multi-domain 5G deployments. It also facilitates the leveraging of installed base. SRv6 MicroSID was introduced at IETF in July 2019, and today, only few months after its introduction, I will show you few interoperability scenarios. So, here is our IPv6 network. On the left-hand side, we have T-Rex traffic generator, which is sending traffic that is immediately encapsulated into SRv6 packet by ingress VPP based on a programmed SRv6 microSID policy. On the right-hand side, we have egress VPP, which decapsulates the SRv6 traffic and sends it back to the traffic generator. The traffic generator itself then measures latency of traffic. Latency of the traffic will vary depending on how many devices the traffic is going through. Then we have several microSID implementations connected to the network. We have three different software implementations. The first two, Linux kernel and VPP, are open source. Then we have Cisco SRv9K, which is iOS XR virtual router. Next, we have several merchant silicon implementations. These are Cisco NCS 5500 router based on Broadcom Jericho NPU, Barefoot Tofino, which is a fully P4 based implementation, Arcus device using Jericho 2 NPU, and Marvell provided implementation on their latest Falcon ASIC. Last two available implementations are ASR9K and very recent Cisco 8000. Each is based on different custom silicon made by Cisco. Our IPv6 network provides full reachability to all locators assigned to different devices. All locators are /48 and they are taken from the same public address space. On top of that, we assigned one SID to egress VPP to do decapsulation of SRv6 packets. Here is a small tool to program microSID into ingress VPP and show current path of the traffic. Right now, traffic is flowing directly from ingress VPP to egress VPP. The destination address of the packet is the decapsulation function, we call it UDX, of egress VPP. On the right, we can see T-Rex measuring current latency. Also, we can take a look on Wireshark capture just after packet is encapsulated by ingress VPP. Here is destination IPv6 address and it is without any SRH. Now we can push new SR policy to the ingress VPP to make sure packet goes via some specific path in the network. Obviously in our network we won't only show interoperability among different microSID implementations. So we will try to force packet to go through one open source implementation like Linux, one merchant silicon implementation, for example Marvell Falcon, and one custom silicon implementation, let's take ASR9K. Now we apply this policy to ingress VPP. We can immediately see increased latency of traffic because right now it goes through different paths in the network. Here we can show what happened. Ingress VPP encapsulated packet where destination address is what we call microSID carrier. That microSID carrier has microSID prefix, which is 2001:1100, and 4 different microSIDs. 100 for Linux, 400 for Marvell, 600 for ASR9K, and D00 for decapsulation. Ingress VPP will send such a packet into IPv6 network, and based on known reachability of 2001:1100:100/48, it is delivered to Linux. Linux then performs UN function, which actually changes destination IP address on the packet by removing value 100 and shifting all remaining microsids by 16 bits. Then packet is forwarded according to the routing table towards 2001:1100:400. This is called shift and forward. Falcon performs the identical functions and 9K as well. So finally the packet will reach egress VPP for decapsulation. Let's take a look on a packet just after ingress VPP. Here we can see how the destination address looks like. It consists of MicroSID prefix and all requested microsids. And also we can take a look at the packet just before it enters the egress VPP. The destination address has only prefix 2001:1100:D00, which is egress UDX function. So let's try something more complex, as we want to show full interoperability. We want one packet to go through all devices, for example counterclockwise. Now we have to build more complex packet, as we need to insert 10 microsids in correct order. For one carrier that's obviously insufficient, and we will need 2 carriers. We will need an SRh, and we put both carriers into the SRh. Set the segments left to 1 and copy the active carrier into the destination address. So our destination address will match prefix 2001:1100:300/48, and it is delivered accordingly to NCS 5500. It will do shift and forward. Cisco 8000 will do shift and forward, 9K, SRv9K and VPP as well. Then packet will reach Marvel, and it sees that he's the last microSID in currently active carrier. But he also sees there is an SRh with segments left equal 1. So he will decrement segment left and copy next carrier into the destination address. Then it forwards packet based on the new destination address towards Arcus. Then another shift and forward by Arcus, identical action by Barefoot, and same by Linux. At this particular moment, the destination address is again 2001:1100:D00. So packet is again delivered to the egress VPP and decapsulated. So let's use our tool to program such a path. And with the T-Rex, we can immediately see that latency is increased again as traffic goes along many devices. And using Wireshark, we can capture packet. This time we will do it just before it reaches egress VPP. Surely, here we can see the destination address is fairly simple as always, but packet still has SRh with both original carriers. That's it. We demonstrated SRv6 MicroSID interoperability. We've seen that SRv6 MicroSID is integral part of SRv6, and it just adds few new instructions. It is very simple to implement in software and hardware, as we have 9 very different implementations only 7 months after SRv6 MicroSID introduction. It keeps all the SRv6 simplicity, and it addresses 5G hyperscale deployment scenario. If you want more information about segment routing, you can buy one of these books. You can follow us on social media, and best source of latest information is always segmentrouting.net. Thank you very much for watching this video. Also, thank to many contributors to this demonstration. Feel free to put any of your questions or comments below this video. Goodbye.